Our next trend is ionization energy. Ionization energy kind of gives itself away with the words itself. It is the energy it takes to form an ion, but more specifically, the energy it takes to make a cation. Remember, a cation is losing electrons, but atoms don't just lose electrons without some energy involved. And so ionization energy is the energy in kilojoules that is needed to remove electrons from the outermost energy level of an atom. And for some atoms, this is a great number, and some it's not as much. And so we're going to see a trend or a pattern with that. And so as we look on the periodic table, as you move up in a group, as you move in a group or move up in a group or a family, you're going to see the amount of energy increases. And the reason is those electrons are closer to the nucleus, and so those proton pull is going to be more. So it's going to take a lot more energy to remove an electron from something that doesn't have very many energies versus something that has like 7 shells, and then it wouldn't take very much to remove an outermost. So it's going to take more to take electrons away from hydrogen than like francium. And then it's going to increase as we move to the right on the periodic table. Same thing, that's a smaller atom closer to the nucleus. So if you can see, this trend is completely opposite that of radius. So this one is up and to the right, where radius was down and to the left. And so the way we use ionization energy, we use it actually to predict the oxidation numbers. Now, we've already gone over the trend. The alkali metals, they try to lose 1, so they're a +1, and +2 for the alkaline earth metals, etc. But we're going to look at some numbers and see how we're going to use these numbers to predict. And we're going to look for a large jump in energy. So this is just giving a good visual. It's got the actual numbers, but you don't have to know that. You can see that the trend as we move to that top right corner. So notice these noble gases, they're very high. In fact, they're higher than any of them. Why would that be? Well, because their shells are completely full. So it's going to take a huge amount of energy to try to remove electrons from them, which is why they don't form cations. So if you'll notice, the trends is moving this way. And so the trend is up and to the right, helium being the most. And so I just want to show you on this, and then I'll show you how we're going to use this. So what you're looking at here is some kilojoules per mole. You don't care about the mole for atoms. And so this first column is what we call first ionization energy. This is second. This is third, fourth, fifth, etc. Okay, and so this shows amount of energy it takes to remove the outermost electron. So you can see it takes almost 496 to take from sodium. So to take a second one from sodium, it would take 4,560. That's a huge difference in energy. So sodium is probably willing to lose an electron based on this, but probably not willing to lose a second, which is why we predict sodium as a +1 cation. If you'll notice, to take one of magnesium's, it takes about 738 kilojoules of energy. To take a second one, which we know that magnesium can lose too, takes about double that amount. Remember, the atom gets smaller when it loses. But to take a third, we got a huge jump in energy here. So this is probably not going to happen here. So we probably predict it will lose just 2. So that's what I meant when you're looking for the large jump. Look, 578, 1820, 2,000, and then we get 11,000, which is why we predict +3 for aluminum. So that's how we use ionization energies. We see where there's a large jump in the value, and we can predict the oxidation number of the cation. We can't predict anion. There's another trend for anions. Let's look at some examples. I'm not going to actually give you a real element because it's very easy now to just look on the periodic table and see what the oxidation. So on your test, I'll just give you a mysterious element X or element Y and see if you can predict the oxidation number. So here we've got element X. To take out one of its electrons, we're going to get 200 kilojoules. To take a second, it's going to take about a little bit more than double, 450. That seems reasonable. To take the third, we're going to need 7,580. This is one that's like, probably not going to happen. Probably not going to happen there. If you can't take the third, you can't take the fourth. So we would predict this element to probably only lose 2 of its electrons. So it would make a positive 2 charge. Okay, so we use those numbers to see where that big jump, when that big jump happens, it's not going to happen. All right, let's look at element Y and see if we can predict its charge. 900 for 1, 9,500 for 2. Probably not going to happen, probably not going to happen. None of those after that's going to happen. So we're probably just going to lose the 1, and so that would just be a 1 positive. So then that's again how we use ionization energy.